Antarctica. It's stunningly beautiful. It supports a vast array of life, and it regulates climates globally through the world's oceans. This vast system works because of a substance so complex, so versatile, that it's been called a chemical freak, H2O.
How does the water molecule drive so many intricate systems of life? And how did we get water on this planet? And in the first place? An accident of physics? Fine-tuning by some great mind? Now there's a big question.
We'll visit the Great Southern Ice Block to look at things the water molecule does and talk with scientists who see it as too good to be a product of chance.
This just didn't happen. This is all shaped by fundamental quantum mechanical properties of hydrogen and oxygen, and these were determined right at the beginning of the universe.
And a leading atheist who sees it as just lucky.
No way that it's fine-tuned. It's a natural property of our universe.
Some say we're accidents in a universe born by chance. Some say we're children of God. I'm Grenville Kent, a Christian academic, and the new atheists have got me questioning my faith. So I'm going wherever the questions take me with my ever-curious son, Marcus, and talking to leading thinkers on both sides of the God question.
Because I really want the evidence. Is there a God?
And will I ever find a hat that fits? Just how impressive is the water molecule? And does it suggest there's a God? Many thought so in ye olden days, when real men with real mustaches said goodbye to real women and went out to explore.
Bound for a realm of wonderment, enchantment and mystery.
Exploring for God and King and good old curiosity. We would link man and machine. Spurred on by the spirit of these pioneers, we would endure any hardship on the road to victory. Actually, we wondered if we could handle the cold.
So we practiced.
We flew to Chile and saw some of the global influence of Antarctica. One thing it causes is the world's driest desert.
You can see those fluffy clouds about 1,600 metres below us, about 1,000 metres above the Pacific Ocean. And that's about where they stay, because there's a cold current coming up from Antarctica, up the coast of Chile and Peru. It's called the Humboldt Current, and it keeps the sea temperatures so low that a low pressure system forms, and the clouds basically don't budge. They don't come up here and bring rain. And that's part of what's caused the Atacama Desert, the highest and driest desert in the world.
Via Buenos Aires, we flew to the coccyx of South America, Ushuaia, the town at the end of the world. These mountains form the spine that connects with Antarctica, and we wanted to look where our journey would take us the next day.
Down there is Ushuaia and the Beagle Channel running to the east. Turn right, head south, Antarctica's that way.
The next morning, we headed to the docks.
We were happy to find our ship didn't have sails.
The Beagle Channel was a gentle introduction, but worse was to come.
The stormiest ocean in the world. Writhing and plunging in the mountainous seas of the roaring Forties, as storm succeeds storm for 2 weeks.
Breakfast is trouble, always a bad weather.
The Antarctic or Southern Ocean has some of the biggest wind events and storm systems on Earth, creating massive hazards for ships going to Antarctica.
Everyone is becoming weary of the stormy seas and the constant motion of the ship.
It's the end of our first full day on the open sea, the Drake Passage. Haven't eaten a thing. Been bending over the rail about 3 times. And I'm lying here, can't lift my head, weak as a kitten. How are you doing, Marcus?
But with new seasick medication, we found our sea legs, just as we were crossing the Antarctic convergence.
The sea temperature has just dropped from 5 to about 1.5 degrees Celsius in the last couple of hours, which means we've entered the Antarctic convergence. That's a really important line on the map where the northern, warmer water meets the cold, dense water coming up from Antarctica. And the species of animals change there. Plankton, fish, birds, mammals, all different once you cross into the Antarctic Ocean, which is this bottom 10% of the world's oceans.
The Antarctic Circumpolar Current is the world's largest flow. It's 150 times larger than all the world's rivers combined. And it influences climates globally, redistributing heat and driving patterns of temperature and rainfall. This ocean circles the globe without land to block it and connects with the Atlantic, Pacific and Indian Oceans. Your first glimpse of the Antarctic continent is unforgettable. I wanted to get down amongst it.
Reverse. Full steam ahead, Captain.
I hit an iceberg on my first voyage, but it turns out that ice is our friend. Without it, life would be hard to imagine. Those guys are enjoying a nap on some sea ice. And sea ice is really important to life in the ocean below. It acts like a blanket. It means that the cold winds freeze the surface of the ocean, but down below that, the water is relatively warmer, and all sorts of amazing life forms can survive down there. There are rich ecosystems down below the ice: algae, krill, fish, supporting a huge food chain, and freakish species that look like they came from some other planet. And all this life depends on a quirk of chemistry. Most chemicals shrink when they freeze, but water expands. It's a freak, the only non-metallic substance to do this. And so ice floats. Antarctica is often called a desert. It holds 40% of Earth's fresh water, but in frozen form, so it's about as dry as any desert. To see how fine-tuned the chemistry of water is, we went to see a chemistry researcher. We had some adventures on the way, but we managed to focus on what we were there for.
Why is ice lighter than water?
Water is H2O. That means it has 2 hydrogen and 1 oxygen, and it's organised like a little boomerang. So you have hydrogen, oxygen, hydrogen. And the thing that happens is that the electrons aren't shared evenly. So the hydrogen doesn't have quite as many as it would like, and the oxygen ends up with more than it perhaps deserves. And so it ends up that this part of the molecule is slightly positive, this slightly negative, slightly positive like this. And then you have the attractions, because of that, between the different water molecules. So this water molecule will be attracted to this one here, so you'll have your little negative bit attracted to your little positive bit. And these extra forces are what helps water to be a liquid at room temperature, unlike something similar like H2S or something like that. And what that means also is when it freezes, the little boomerangs will line themselves up into a lattice so that they're all facing each other the right way, and that makes water less dense as a solid than it is as a liquid, and that means that the ice will float to the top when it freezes instead of sinking to the bottom.
Scientist and Christian theologian Alistair McGrath has written about the fine-tuning of water.
Ice floats on water, thus creating the capacity for life to exist underneath ice. Life as we know it depends enormously on these unique properties of water.
That little iceberg reminds me that if the laws of physical chemistry were slightly different and ice sank rather than floating in water, then it's hard to imagine life on this planet at all. So if water and all the other elements just blew out the back of an exploding star, a totally mindless, random process, then why is it all so perfect?
We haven't always fully appreciated the animals in Antarctica, but they are major fauna in the ecosystem. Perhaps we didn't realize just how much our lives are linked with theirs. It's no exaggeration to say that water plays the starring role in life, theirs and ours. It acts in so many of the chemical reactions in our bodies. These animals use it to keep their blood fluid or runny enough to flow. It's in their brains and nerves because it dissolves ions.
The cells are the basis for life and the membranes around the outside. And the cell membrane is made up of a whole lot of molecules that have one end that really like water, they're hydrophilic, and the other end that really doesn't like water, which we call hydrophobic. And so what they do is they organise themselves in two layers. So you have all the heads on the outside, around like this, and then all the tails pointing in together where they can get away from the water. And then so the heads are organised where they're facing the water. And they're not bonded together. It's more like that they're just in their mutual attraction for water or dislike for water. And that's enough to form the membrane for the cell, but it is actually quite flexible. They're not held in one place and they can move around all around the cell, in fact.
One of the remarkable things, for example, is the structure of the cells that make up our bodies and indeed the structures of most biological systems. There's a very complex interaction within them between hydrophilic and hydrophobic. In other words, those parts of systems that love water, those that want to repel from them. And actually, water plays a critically important role in sustaining not simply biological processes, but biological structures as well.
Water helps proteins to fold correctly, the proteins that make up our bodies.
Proteins are long chains of amino acids, and the amino acid sequence is actually determined by your genes. But it's not just enough to have the right sequence, they also have to have the right shape. There's bits of the protein that like water and bits that don't, and that helps them fold up in the right shape. If it's not folded correctly, it won't work at all.
Our biological processes involve water.
In my research, I look at the enzymes and the way that they're put together. And what you find is very often that if you just change a little thing, the enzyme doesn't work at all, or perhaps it does something completely different. That's really fascinating to us because we think, wow, it's so precisely put together. And very often you have a water molecule in there participating as well.
Why is water so good at dissolving things?
That's partly because it's what we call a polar molecule. It has regions of positive and negative charge within it, which allows it to dissolve other polar molecules. And also importantly, it allows it to dissolve things called ions or your salts. And that's really important for your body because you need to be able to transport minerals in your blood, which is mainly made up of water. And then you've got other situations like the dissolving of carbon dioxide in the oceans. And so you have the solvent properties of water being important for life on many different levels.
One of the remarkable features about water is its ability to act as a solvent. And I don't just mean something that's able to take up various molecules that are significant. I mean it's able to do things with them in solution, which means that various biological, physical, and chemical processes can take place precisely because water is such an effective solvent. Water makes things happen.
I had no idea how many plants live in the ocean and how important they are to our lives.
There's a lot of plant life in the ocean. In the oxygen levels in the atmosphere, that oxygen is produced by plants.
One little marine plant, the coccolithoform, produces about half the oxygen in our atmosphere. If it's damaged, say by ocean acidification, we're in huge trouble.
The oxygen, if you like, in every second breath that we breathe has come to you thanks to a marine plant.
Water plays an intricate role in the incredibly complex chemistry of food production, photosynthesis in plants.
Photosynthesis is the process where you take carbon dioxide water and then you convert it to glucose and oxygen. And that happens with sunlight in the leaves of plants, for instance. Also, you can have that happening in the oceans. And what happens is you're taking the energy from the sun to convert it into glucose, and then that's a way of storing the energy so that you can use it later. So when you eat it, for example, you're converting it back into carbon dioxide and water, and you're using the energy. And you need water for that process, so it's very important.
And water has another chemical quirk.
Well, if you have your look at your glass of water, you'll notice that the surface of the water goes up at the edges, and that's because the water is actually attracted to the glass walls. And if you have a really small tube, a capillary, in fact, the water will rise all the way up the tube against gravity because of this attraction between the water and walls, and it pulls the rest of the water with it.
This is one factor that helps water reach the top of trees, making tall trees possible with all the food and oxygen that they supply. Again, water's properties are crucial to the ecosystem that supports our lives.
Woo! Summertime and the living is easy. Woo! Oh yeah, that's cool. That is not too bad. I highly recommend Antarctic swimming. Oh, not that.
Someone had iced my hat.
It's obvious to say that if you're wet in the wind, your temperature drops rapidly. But that is because of the high latent heat of water. Chemistry, baby.
The chemistry of water keeps our planet's temperatures right for life. Professor Matthew England is a leading oceanographer and climate researcher.
The great thing about seawater is that it's got an incredibly high capacity to store heat. Having an ocean almost covering the planet means our seasonal cycle's less extreme, our temperatures at the high latitudes are sort of somewhat milder than they'd be. The tropics are not nearly as warm as they'd be without oceans, but also under global warming, as greenhouse gases increase and warm the planet, a huge amount of heat is being absorbed by the oceans. In fact, if you go looking for where all the heat is from our increase in greenhouse gases, 90% of it is held by the oceans. If we had a planet with no oceans, the atmosphere would already be many more degrees Celsius warmer than it is.
Ocean currents spread heat and help even out global temperatures.
When people talk about the ocean global conveyor belt, they're really talking about a set of currents that help the ocean in its role in moderating climate.
Water is heated by the sun, especially at the equator, and it's mixed worldwide by established currents.
And actually what it's doing is moderating climate. If we didn't have the ocean to provide these services to us, we'd be in real trouble.
Antarctic water is cold and dense and drops 5 kilometres down to the bottom of the world's ocean. This Antarctic bottom water then flows globally, well into the northern hemisphere, and helps drive climate.
Because of its formation at the surface, it's rich in oxygen. It's a very important way of what we call refreshing the very deep part of the ocean. We call it ventilation. The water is a very curious substance in the fact that its heat capacity is just so very large.
In Antarctica, Marcus, even with no facial hair, soon showed he was a real man.
I was curious to see how cold it was and if I could handle it.
Water is a brilliant temperature regulator on this planet because more than almost any other chemical, the water molecule naturally loves to keep a nice, steady temperature, and it takes a lot of energy to shift it. So if you think of heating up water for a hot drink, it takes 10 times as much energy as heating up, say, a lump of iron of the same weight.
One of the remarkable things about water, again, is its ability to sustain a climate such as ours, with its very significant specific heat. It's able to actually act as a shield to enable atmospheric processes to take place. And again, without water, you and I'd be in some difficulty.
The chemists would say water has a high latent heat and a high specific heat capacity. But that basically means that the 65% of water in our bodies and the 1/3 of water on our planet's surface is really important in keeping temperatures stable and avoiding the extremes that might otherwise have happened. So it's lucky we've got so much of it. Or is it lucky?
And then there's carbon.
The ocean absorbs carbon from the atmosphere, and plankton photosynthesize with it, a bit like trees do on the surface, turning waste carbon into a food source for a vast ecosystem down there. It's part of what we call carbon sequestration, and the ocean holds 50 times more carbon than the atmosphere does, and the Southern Ocean alone accounts for about 40% of the world's carbon. It's a pretty effective climate management system, but human activity is spitting about 6 billion tonnes of carbon into the air every year, and the ocean can absorb only about 3 billion tonnes. And so while we admire the system, we're left with a question: how far can we push it?
For all the carbon that we put in the atmosphere, only about a half of it stays there. And out of the half that disappears, about 2/3 of that goes into the ocean. So knowing what the ocean's doing, where the CO2 is going, and whether that service of taking up our CO2 is going to continue is really crucial to understanding the future of climate.
CO2 and heat simply dissolve into the ocean, and the Southern Ocean mixes most deeply.
My specialty is a biological pump, we call it, because it's a set of processes that pump CO2 out of the atmosphere into the ocean interior. Like any plant, little plants in the sea, they take up the carbon dioxide, they turn it into their tissues. Those things sink, away from the atmosphere into the deep ocean. There's a whole ecosystem that gets involved in that. So the animals eat the plants, and the large animals eat those animals. And so you can imagine that the whole carbon throughput is linked to the whole functioning of the ecosystem.
Did such a complex system come about with no engineering genius behind it? With so much snow, it would have been irresponsible not to use it.
Dude, I'm the Norwegian champion of 1927. Yes!
3, 2, 1, go!
Yes! Oh yes! The old man wins.
Race you down!
Press me down.
Well, we call it a draw. The Antarctic continent is nearly 5 kilometres high of snow and ice, and it averages 2 kilometres thick. That's one big ice cube in the world's drink.
So how did Earth get all this water?
When the Earth formed, the temperature around the sun and the Earth was incredibly hot. The sun was just forming. The temperature in the region was 1,000 degrees. There'd be no free water. But water can be stored in rocks pretty efficiently. And now we've actually realized that there's probably more water stored deep underground in the Earth than in all the oceans. So it could have been that the water came here embedded deeply in small rocks and grains that came together to coalesce to form the Earth, or delivered by rocks as asteroids.
Our solar system began with a superabundance of water. But the water we have on the Earth today is not the same as the water we started with. In fact, we know that because we have analysis of comets, primordial comets, the comets that are left over from that period when planets formed. And those comets have a very different isotope signature for water than we see in the present-day Earth. And so we got our water from a different source than the primordial comets. In fact, today we know that our solar system has at least 5 major belts of asteroids and comets, and research is ongoing as to exactly what source of comets and asteroids gave us the water that our planet possesses today. But one thing we know, we have exactly the right amount of water to make advanced life possible here on planet Earth.
Making chemicals in the nuclear furnaces of stars, which then explode them out into the universe, producing a planet with just the right amount of water and a moon to stir it. Is that all just too clever for blind chance? Do the precision and versatility of water suggest it was engineered by a great mind?
When a chemist thinks about water, we're thinking about it as a consequence of the laws of physics that underpin all of chemistry. And you can ask yourself, did this arise by chance, or was there some sort of genius behind it all?
Many, many other properties of water are not accidental. This just didn't happen. This is all shaped by fundamental quantum mechanical properties of hydrogen and oxygen. And these were determined right at the beginning of the universe. If these had been different, well, water might not be here, we might not be here, but it's the way the universe was set up right from the beginning that determines that water can act in this remarkable way.
Water has an amazing set of properties, that expansion coefficient, the fact that it stores a lot of heat, which is useful on Earth, the fact that it's a polar molecule and can dissolve things, make it very interesting. Well, first of all, it happens to be ubiquitous. But secondly, the fact that we live on a planet that's full of water, which has these unique properties, is more likely to be due to the fact that if it wasn't here, we couldn't be here. There's lots of planets in the universe that have quite different circumstances. It's more an example of natural selection.
Many people have argued that the universe seems to be fine-tuned for life. And I think, as an empirical observation, that's right. The key question is, how persuasive is that? And certainly an atheist would say, well, look, that's just a piece of good luck. It means nothing. It's, the universe had to look like something that looks like that. That's just the way it is.
But the fact that we happen to live on Earth and not Venus or Jupiter is an example of the fact that life can evolve under certain conditions. And with 100 billion stars in our galaxy and 100 billion galaxies in the universe, most stars having planets around them, there's an incredible number of possibilities. And it's natural selection that may imply that life might only be able to evolve on water worlds, but we don't even know that. It could be that exotic forms of life could live on other exotic environments. That's one of the wonderful mysteries of the universe that we hope to find out. But confusing cosmic natural selection with design is the same mistake people made when they used to think life was specially designed for its environment.
I certainly would not want to say that fine-tuning proves anything, but it's absolutely consistent with the Christian vision of things. If you like, God has set things up so that it's maximally guided towards its intended outcome. That's not about proving anything. What we're saying is, look, here's the Christian way of looking at things, here's this observation, and you know, it fits in easily and naturally into that. It's about the scientific implementation of a theological vision.
So from all of this, my conclusion has to be...
Humble old H2O. You rarely think of it, and yet it's an elegant molecule, chemically fine-tuned for literally thousands of reactions that support life. It looks like a work of genius. And could it be a subtle clue to a kind intelligence who wants us to be alive and to enjoy ourselves? What do you think?